In the last section, we applied the Schrödinger equation to 1D box model. One example is a conjugate system. We showed that only certain energies are allowed, and we say the energy is quantized. Both energy and the wave function are determined by a quantum number n. In this section, we're going to talk about more systems. First, let's look at a free particle in a three-dimensional box instead of one-dimensional box. The wave function now includes three variables. Here is the Schrödinger equation for the free particle in a three-dimensional box. The wave function can be written as a product of three individual wave functions. Each of them has one variable, x, y, z. And the Schrödinger equation can be separated into three individual Schrödinger equations. Solving these three individual wave functions and then combine them together give you the solution of the total wave function and the total energy. Not surprisingly, both wave function and the energy depends on three quantum numbers: nx, ny, nz. All these quantum numbers are integers, 1, 2, 3. And therefore, if we want to determine one wave function of this three-dimensional box, you need three quantum numbers. So nx, ny, nz. Similarly, the energy is also determined by three quantum numbers, nx, ny, nz. The A, B, C are the dimensions of the box. Let's look at the equation for the total energy of the three-dimensional box. If the box is a cubic, then A, B, C are the same. Therefore, the energy now becomes this equation: h squared divided by 8ma squared, nx squared, ny squared, and z squared. These are three quantum numbers. Here is a plot of the energy levels. The lowest energy is when quantum number nx, ny, and z are all 1. This gives you the lowest energy. Again, this is non-zero. Lowest energy is non-zero, so it's a 0-point energy. What about the energy above it? That means if one of them is 2. So for example, when nx is 2, ny is 1, and z is 1, then nx squared plus ny squared plus nz squared is 4 plus 1 plus 1. That's 4 plus 2, that's 6. So this added together is 6. However, when nx is 1 and y is 2 and z is 1, when you add together squared, you also get 6. Similarly, when nx is 1 and y is 1 and z is 2, you also get 6. In other words, these three combination of nx, ny, and z give you the same energy. They are at the same energy. Now, this combination of three quantum numbers give you different wave function because nx are different, ny are different, and z are different. So when you plot the wave function, they are different. That means they are in a different state, but they have they have the same energy. And this is very common in quantum mechanics, and this is called degeneracy. Degeneracy is several states have the same energy. For example, for hydrogen atom, we learned that you have 2px, 2py, 2pz. Okay, 2px is along x direction, 2py along y direction, 2pz along z direction. So they are different wave function, but they have the same energy. These all have the same energy. They are degenerate. Right? This degeneracy you can see is only when A, B, C are the same. So symmetry introduces degeneracy. Let's look at an example. For a particle in a cubic box, A equals B equals C. What is the degeneracy of the energy level E equals 6h squared divided by 8ma squared? For a cubic box, we know from the last slides, the general energy equation is h squared divided by 8ma squared, nx squared, ny squared, nz squared. It's determined by 3 quantum numbers, nx, ny, and z. These are the only allowed energy levels. So this must be one of this. For this to be the same, that means this equals 6. And x squared, ny squared, and z squared equals 6. So how do you make an x squared, ny squared, and z squared add together is 6? One possibility is this is 1, and this squared has to be 1, and the other one can be 4. Okay, so 4 plus 1 plus 1 is 6. All right, and that means this is 2, and z is 2. 2 squared is 6. So you have 1, 1, 2. What are the other possibilities? 1, 2, 1. 2, 1, 1. Then when they square add together is 6. These are the only 3 possibilities. And therefore, you have the degeneracy is 3. So the 3 wave function you put into the wave nx, okay, here nx, ny, nz, 1, 1, 2. So you see 1, 1, 2. That's when nx, ny, and z is 1, 1, 2. Now what about 1, 2, 1? So here 1, 2, 1. And this is 2, 1, 1. And you can see these 3 wave functions are different. When you plot it, you get different shape. But when you calculate the energy using this equation, you will get 6. And therefore, they are degenerate. In the particle in a box model, we assume the particle is free inside the box, potential energy 0, but at the 2 ends, the potential energy suddenly becomes infinity. And this will ensure the electrons or particles can only move inside the box, but not get out of the box. Now, let's look at this situation where potential energy is not infinite, but has a value that is greater than the total energy of the system. So it's greater than E, but not infinite. So what happens to the particle? Okay, imagine in a classical system, let's say you have a ball moving around the 2 hills. So you have a ball moving. So if the potential energy here, mgh, okay, this potential energy is greater than the energy of the ball, then it can only move here back and forth, back and forth. It cannot escape from this trap. This is a classical view of the particle. What happens to the quantum mechanics? The particle moves freely inside here, but you have a high potential energy on the 2 ends. So we are going to solve the Schrödinger equation and see what is the wave function outside the box. So this is the wave function inside the box where there's no potential energy, but outside the box, you have a potential energy here is non-zero. Okay. Now this one we already see. This is a free particle. The solution is the same as we did before. Okay. A e to the negative ikx plus b times e to the positive ikx. Now at the 2 ends, the solution looks similar. All right. but the K is different. And we're going to skip the mathematics, and we're applying again boundary condition. In this case, give you the wave function outside the box. Here are the two wave functions outside the box. And it's easier if we look at the plots. So next slide. Here are the plots of some of the allowed wave functions. Let's compare with the 1D box model where the potential energy becomes infinity at the two ends. So the first wave function is like this. At two ends, it goes to 0. And the second one also goes to 0 at two ends. The third one also goes to 0. So you see, the wave function inside looks very similar to the 1D box model when the potential energy is infinite. But at the two ends, they are not 0. For example, here. So it should go to 0, but here it's not 0, but it can exponentially decrease, extended into the wall. So outside the box decays exponentially non-zero wave function in classical forbidden region. These are the walls where potential energy is higher than the total energy. So in classical physics, they are forbidden region, but the wave function is non-zero inside. Okay. So imagine the wall is not very thick. Let's say here. Then the wave function decays slowly at the other end of the wall. It's not 0 yet. 0 may be somewhere here, but it's not 0 at the end. And then outside this wall, it becomes free again. So here, because it's a free particle outside, so it will oscillate with this amplitude outside the box. In other words, the particle actually escape from this energy potential and get out of the box. So here is another drawing. You see this is inside box, and this is a very thin wall with a potential energy greater than the total energy, and the wave function decrease slowly and non-zero here, and then potential energy becomes 0 again, so it oscillates outside. And this gives you the probability. So you have the probability that the particle get out of the box. So in quantum mechanics, the particle leaks into the barrier, and this is called the tunneling effect. The ability of particle to penetrate into and possibly pass through a classical forbidden region is known as tunneling. Again, let's look at the tunneling effect. Here is the free particle, and here you have a wall with potential energy greater than E, so the wave function decreases exponentially. Now, if this wall is not too thick, then at the end of the wall, the wave function may not be 0. It's non-zero at the right side. According to this equation, the wave function at this side should be A, E, negative K. X is the length. So if length is A, then it's Ka. So that's the wave function at the right side. The probability of the particle on the right side should square of this thing. And that gives you e to the negative 2Ka. Now what is K? K is the square root 2m v naught minus E divided by h bar squared. So v naught is the potential energy of the wall. E is the total energy of the system. Now, according to this equation, the smaller the A, because you have a negative sign, so smaller the A, larger the transmission probability, the more possibility the electrons will go out if A is small. So the thinner the wall, the more probable the electron will go out. Also, again, because of negative sign, the smaller the mass of the particle, the more possibility the particle get out of the box. And therefore, the tunneling effect is very important for small particles like electrons, moderately important for protons, and less important for heavier particles. One of the applications of tunneling effect is scanning tunneling microscope. The key of this instrument is this metal tip, and this is made of one atom. And here is a surface that we want to measure. And the electrons can jump from this metal tip to the surface of the sample by tunneling effect. And the current depends on the gap, energy gap, A. The smaller the A, the larger the current. So when we scan along the surface, all right, for example, if there's a bump, okay, let's say here is a bump, then the gap suddenly becomes smaller, and that will give you a large current jump. So you see a current jump, and this is because you have a bump here. Now, if somewhere you have a missing atom, then the gap becomes larger, and then you see a larger gap, a smaller current, so current decrease. So by measuring the current of this tunneling effect, the computer can analyze and give you the profile of the surface. In this example, we are going to calculate the current change when the gap change from 0.2 to 0.3 nanometer. The difference is about 0.1 nanometer, and that is about 1 atom thick. So when the gap change 1 atom thick, how much current change? Okay, we are going to calculate the ratio. So the current when the gap is x1, let's say this is x1, and current when the gap is x2. Okay, according to this equation, so it will be a squared exponential. Now let's combine all these as k, so negative 2k x1 a squared e negative 2k x2 a squared cancel, so e the power should minus 2k x1 minus x2. Okay, x1 minus the power difference. So this is about 0.1 nanometer, so that times 10 to the minus 9. Okay, 10 to nanometer 9. So it's 1 times 10 to the minus 10. And that gives you 10 to the minus 10. And so you plug in all the data, and the answer is 8.8. That's a huge change. 1 atom change in the gap give you current change 10 times. And this shows how sensitive the tunneling microscope is when the surface change 1 atom thick.